Hello everybody and welcome back to another visual pattern challenge. Here's our pattern today. Here's step 1, step 2, step 3, and your challenge is to predict the number of hexagons in step 4. This is a difficult one. If you can get step 4, can you get step 43? And can you write an equation that could be used to get the number of hexagons in any step at all? I think this may be the hardest one we've ever had. So however far you can get, give it a shot, pause the video, and see how it goes. All right, so right off the bat, it looks like it's growing pretty rapidly, and I can tell it's not going to be linear because we keep putting rings on the outside. So those rings have to be getting bigger in every step. So this can't be a steady linear rate of growth. So my guess would be quadratic, but this odd pattern of hexagons, and then the hexagons are arranged in an odd way. I don't know what this is going to be. We've got a pentagon made up of hexagons, basically, is what's happening, because this is a five-sided larger figure. Well, why don't we count, or just see what we can see is going on here, and maybe count the length of the sides to see if we can cobble together a good guess for step 4. So I think I'm going to think about this as a side, this sort of bottom, and then these two arms here as a side, and then I guess I'll think of these two as sides and that as the top piece. Let's see how this goes when you look at the next step, the next ring out. So this side goes from 3 to 4, and this side, goes from 3 to 4 to 5. So I would expect we'd have an outer ring of 6 here, of at least of that side. And then let's look at these two kind of arms here. So they're 2, and then they're 3, and then they're 4. Okay, so this seems to be following a regular pattern here. So these then, if they're 2 and then 3 and then 4, they should be 5 and 5. Okay, let's look at this. These are 1, and then they become 2. Okay, good. And then 3, so these should be 4. And then that's 1, 1. Oh, so it's always 1 at the top. Okay, so this does not give us the number in step 4. This gives us the ring that we're adding. We're going to need to count up how much we had before that. And I think we might as well make a chart while we're doing this, since we're going to be doing the hard work of counting. So we'll put in the step number and the number of hexagons. So let's see, 3, 4, 5, 6, 7, 8, 9, 10. So in step 1, we're starting with 10. In step 2, we're going to add 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 more. So we're adding 15 to get up to 25. And since we're adding 15, I know the difference is going to be 15. So I'll just fill that in while I'm at it. Let's go to step 3. So here we're starting at 25 and we're adding 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We're adding 20 more. So 25 plus 20 would be 45. Okay, so I would expect then for between step 3 and 4, we added first 15 and then 20. So I'm guessing we're adding 25. Does this add up to 25? So let's see, 6 and 5 is 11, and 5 is 16, and 4 is 20, and 5 more. 4 and 1 is 5. So we're adding 25. Okay, so the pattern does hold here. That's great. So 45 plus 25 is going to be 70. All right. Well, it seems like we've got our pattern worked out, although this number is not a constant, so we're going to take the difference of the differences. So 15 or 20 minus 15 is 5, and 25 minus 20 is 5. So it looks like it's going to be quadratic because we have a constant in the difference of the differences. But this number, you have to divide it by 2 to get the leading coefficient of the x squared term. So we're going to have 2.5x squared as part of this equation, which seems kind of difficult and weird. Well, let's fill in our 70 for step 4 because we've predicted that. And how can we approach figuring out an equation with that? I think maybe I'll do this as a fraction instead. 2.5 is 5 halves x, 5 halves. So I'm going to write 5x squared over 2, and then maybe there's something else that also will be over 2. What would we have to add? So in step 1, 5x squared would be 5. All right, so we would need 5 more. Oh, but this is going to be divided by 2. So on the top, we want to get to 20. If the whole thing's going to be divided by 2, we want to get to 20. So if we have 5x squared, we're going to need 15. So this is a candidate for the equation because it works with step 1. We put in 1 here. 1 times 1 is 1 times 5 is 5 plus 15 is 20 divided by 2 is 10. Does that work with step 2? So we'd have 5 times x squared, or 2 squared would be 4. So 20 plus 15. I can see that's not going to work because that's going to be an odd number on the top, and we're going to get a 0.5. So maybe instead of 15, this is times or plus 15x. Let's see if that works. It's still going to work with step 1, right? Because this is just 1 in step 1. How does it work in step 2? So 5 times 2 squared, so that's 4, plus 15 times 2, that's 30 over 2. 20 plus 30 would be 50, divided by 2 is 25. Aha, so that does work for step 2. Let's just test it with step 3, just in case. So 5 times the step number squared, so that'd be 9, plus 15 times the step number, so 15 times 3 would be 45, and all that divided by 2, and 5 times 9 is 45, 45 plus 45 is 90, divided by 2 is 45, so this is working. This, I think, is pretty hard to arrive at, and I did it by a little stumbling around in the dark, a process of trial and error, but I think that works. One thing I would recommend, if you stumble around towards an equation like this and you get it, you might want to test it. Or if you get absolutely stuck on this step, you might want to go to a tool like GeoGebra to graph this. So let's actually see if we're correct here. What I've done, actually, I set this up ahead of time. I put in the points we had, A, B, and C here. And then we're going to use the GeoGebra fit poly command, and we'll put in our points A, B, C, and see what happens. And what we got is 2.5x squared plus 7.5x. That would be 5 if you multiplied both these by 2. 5x squared plus 15 all over 2. So that does verify what we came up with there. Now, trying to plug in step 43 in here is annoying. And since we're already in GeoGebra, here's what I'm going to do. I'm going to make a line, x equals 43. And then we're just going to go find the intersection. So we'll put that in, and then this is going to be way up here. Whoops, now I'm zooming in. Let me zoom out even more so we can move rapidly along this line here. And I'm trying to find the spot where this line x equals 43 intersects our other function. And here it is. GeoGebra plots that for us. So the intersection point x equals 43 and y equals 49, 45. So what that means is that's the number of hexagons at the step x equals 43. It's 49, 45. So in step 43, 49, 45, 4,945 hexagons. Well, I think this was just an absolute bear of a pattern to do. Did you get step 4? If you did, I think you should feel pretty good about yourself. Did you get any further than that? Congratulations, I applaud you. Let me know how it went. Thanks, everybody.